Okay, cool. Great use of our efforts in AI. We should perhaps put them towards other purposes. I mean, eventually, of course, we want to be able to see robots or machines be able to understand the world similar to how humans do. And this involves, of course, a general understanding of the semantic labels for object parts, how they move around, and how they can be interacted with from a perspective similar to that of a human. So let's maybe consider a simpler problem formulation, which is the 3D perception just from a 2D image. And so if you as a person, despite the fact that of course this image is 2D and we in general scenarios, we as people do have two eyes and we can perform a bit of stereo to get a 3D understanding, it's still very much possible to look at this 2D image and estimate the geometric structures of the objects that are in the scene, even accounting for things like occlusion, and the fact that we see only this projection. So how can we imbue, vision systems with this kind of learned knowledge as well? So I think one nice opportunity is basically to leverage the large amount of synthetic data that we have of 3D objects, and take this as basically just a strong prior. So let's simplify the problem down to an object by object basis and try to retrieve and align, a similar object into the image to represent that object structure. So here we can, in the end, produce an object-based lightweight representation based on these existing valid kind of models that already come from a data set. So if we take as a basis these kinds of synthetic 3D objects, we want to be able to, of course, we first detect these objects in the image with state-of-the-art instant segmentation techniques. And then we can take the detected objects for each object, embed them into a space where they lie together with synthetic 3D objects, where geometrically, structurally similar objects lie close together, despite the fact that they might come from different sources, like the 2D image or the synthetic domain. So this embedding space allows us to perform retrieval just by taking a nearest neighbor query for an image representation of an object to find the closest synthetic object that's being represented here. And then simultaneously, we can also predict the alignment of that object geometry into the image so that we can get finally as output a set of aligned synthetic objects to the image that actually represent the objects that are being seen. So what we did to take a look at this particular problem is to try to learn this image shape embedding space such that we can learn across these two fairly different domains. And so the image space is being represented by strong features that are learned from image segmentation, instant segmentation approaches, being influenced by their box and mask, and the synthetic objects. In order to put them in kind of a similar representation, we use rendered versions of the 3D geometry. In this case, we don't have any texture. But here we see also kind of projected views of the objects, and then we try to map them into a shared space. So from these kinds of features, then we can also predict the pose of the object as the object center and the rotation. So here we can take a look at the image shape embedding space construction. And so this is being constructed by a contrastive loss formulation, where we want to basically take supervised information about which 3D shape corresponds to which part of the image. And those that are corresponding should lie closer together. Those that don't should lie further away from each other. And then we also have the prediction of the pose here as a rotation. This is a Turnian representation where we do a classification for the rotation, and then a refinement in terms of a regression on top of that in order to get the orientation of the object. And then finally, the object center is an offset basically from its predicted box in the 2D space. So this allows us basically to map between these two domains and retrieve objects and for reconstruction. So we can also measure this in terms of the reconstruction performance. So this is in comparison to Mesh RCNN, which put out the first work to understand images in this kind of particular object by object formulation with the center and the orientation prediction here. And so Mesh RCNN is a generative approach and doesn't actually perform retrieval, which allows for it to have some more flexibility. On the other hand, the retrieval allows us to actually always retrieve valid objects up until the data set quality, basically. And in fact, if we perform a reliable retrieval and alignment that we see being evaluated here in terms of the Mesh AP, we can actually get an improved reconstruction error from even this kind of retrieval-based approach. So this is on the Pix3D data set, and you can see some visualizations of the retrieved objects here. And so we are capable of sort of regularizing the space down to these basic object primitives. And that allows for a fairly reliable retrieval that doesn't necessarily consider even the opportunity of not necessarily fully generating a table leg down to the bottom. So the other kind of nice part about this retrieval-based approach is that we can, if we acquire more synthetic objects, we can simply re-embed them into the space for nearest neighbors. And that allows us to have a potentially more accurate reconstruction as we expand the diversity of the database here. So this is adding additional synthetic objects at inference time, just adding them into the image shape embedding space. To be fair, they are all of the same class category as what was originally trained on. So this is basically adding some more geometric diversity into the database for retrieval. And we can, in fact, get an improved performance by just adding additional CAD models then into the database. So we can also take a look at this retrieval really as reconstruction. So here we have ground truth 2D detection, and we don't worry about that part, and simply evaluate the quality of the reconstruction as with respect to the retrieved object. And this is being evaluated by time for distance as well as F-score. In this case, we can still produce a more accurate reconstruction based on this retrieval-based approach. And so you can see, again, the embedding space that we construct here. And this is structured such that the synthetic objects, you can see the renderings gray on the black background. They all kind of clustered together with images that are similarly structured. So here we have like round tables, and here we have more like shelf-oriented tables. And the standard kind of rectangular tables are all grouped here together. So we do learn the space that's structured such that we can actually map together semantically or geometrically similar objects into a similar neighborhood. So I think this is pretty nice, but to be fair, I think the results that I've shown, they're on sort of simplistic kind of data. So you see here, there's mostly one object that's being seen primarily in the image. And what happens when you encounter more real world scenarios, we have typically far more objects, and we have occlusions and a lot of clutter in these kinds of environments. So we also might not necessarily have very exact matches to the geometry that's being seen in the database. So we want to be able to still leverage these kinds of priors in terms of retrieved shapes from the synthetic database, these CAD models, but we want to become more robust to these kinds of scenarios where we have these kinds of occlusions, inexact matches, and so on. And so what we want to do here is to take a sort of patch-based approach to understanding an object. So there might not be an exact object in the database that has precisely this particular kind of geometric structure, but there will probably be some that have a similar kind of tier back or a similar kind of tier legs. And we can look to these kinds of features to find one that most similarly represents that particular object for the sake of this like object-based reasoning. And so we construct this embedding space actually at the patch level in order to find similar parts of objects effectively. Their patches is just regions in the image space that are being embedded into this embedding space. And then we can perform the shape retrieval based on querying multiple patches into this embedding space in order to find the one that, in terms of a best majority vote, best represents that particular object. So here again, we also simultaneously predict the pose of the object so that we can get that representation that reflects the image space view. So here we have the RGB encoding of the input image similar as before. So an object detection that's telling us the object box and the object mask. And now we have patches that are taken out of RGB space and out of the rendered shape space in order to determine which patches are more similar and which patches are not. In this case, we want to make sure we don't associate things like, if a chair has 4 legs, all of these legs should actually be similar to each other and not different because one happens to be the top left one and the other one is the bottom right one. So we want to understand similarity based on how similar the normals are in world space of the shapes. And so that gives us a similarity metric that we can use for constructing which patches are actually more similar to each other for the retrieval. So here we have this embedding loss construction, which is a contrastive loss where we have A as the anchor patches, P as the positive patches determined by the normal similarity, and N as negative patches determined by those that are not similar. And we have multiple positives for each query. So this constant is basically just balancing the positive and negative ratio. So here we're pulling the patches that are similar into the same location and the patches that are different to be further away. So we use the self-similarity of the normals to determine which patches are going to be similar or not based on the IOU of the normal histogram. And then we can, at test time, vote for which shape is best matching. So we have basically KQ sampled patches from the RGB feature space. And then each of these patches then retrieves KR shape patches, rendered shape patches. And each of these are voting for the shape ID. So out of all of these retrieved, then we can take a majority vote over them in order to get the final shape ID that matches the most of all of the parts of the objects that have been seen. So we evaluate this on the ScanNet dataset, which has images and also CAD model associations from ShapeNet. And so this is in comparison to the previous approach that was shape to shape. And so here, the problem, of course, if you don't find something that exactly matches that particular shape, or you see only some part of it in the image, then you might end up with a less reliable shape reconstruction. So here we end up with a more robust reconstruction in terms of the objects that are being seen in the images. And what that looks like in terms of qualitative examples here, we have some of the images and the retrieved objects from our approach versus the object-to-object matching that we had previously, as well as this is Total 3D is a state-of-the-art generative approach to generate a mesh for every object that's being detected. So this kind of patch-based reasoning allows us to get more reliable representations of objects where there's not something quite exactly that fits in the database. as well as a more robust time retrieving objects that are only sort of partially seen, like this table here in the background of this particular object or image, sorry. And so we have also a few more examples here. Like these are all the same chairs, but unfortunately we don't really have one that exactly matches this one in the database. But we can find a bunch of chairs that sort of match very similar to the structure and style of what's being seen in the image here, as opposed to the larger diversity and assortment of chairs. Of course, we would like them to actually be all the same, but we'll come to reasoning about not independent predictions in a bit later. So we can also take a look at the construction of the embedding space that we get based on this patch-based retrieval, and take a look at the top n nearest neighbors, in this case, the top 8 nearest neighbors. So when we do this kind of patch-based reasoning, local reasoning about these kinds of mid-level features of objects, we can get not only a top 1 neighbor that kind of reflects decently well the object here, but also the rest of the top 8 neighbors are actually fairly similarly structured to the input query, as opposed to the previous embedding construction that was based on the shapes that actually falls off fairly quickly from the top 1 nearest neighbor. You start ending up actually with totally structurally different couches at some point. And similarly here, in terms of the tables, you end up with retrieving some tables that are actually fairly dramatically differently structured, without actually having this more robust, like, local reasoning about the object structures. And of course, we can also evaluate some of this quantitatively. So this is evaluating the shape reconstruction task and not any of the alignment. So here, in terms of the F-score, we can outperform the previous mastic had, as well as Total 3D. And we have a fairly robust shape retrieval versus the top K number of retrieved objects that are being considered in terms of retrieval. So this allows us to construct a nice way to understand the object shapes in terms of retrieval. We didn't really consider much so far in terms of the actual object pose alignment. So of course, that part is also important in terms of reasoning about the scene. And so far we've had basically the orientation, 3 degrees of freedom for orientation, and then 2 degrees of freedom actually for translation, which is not actually the full 9 degrees of freedom that you would like to have in terms of the actual object pose, that it's being structured in relation to all the other objects in the scene. So here we're taking a look at focusing on understanding a more robust object alignment estimation, as opposed to just the shape retrieval task. So we want to be able to get, just from the input image, still a reliable estimate of the 9 degrees of freedom rotation translation at scale of the objects that are being retrieved here. So here, in order to do this, again, we have a 2D backbone to process the input image features in order to understand, which objects are there based on instance segmentation. But then we want to establish a more informative set of features in order to give us information about the object alignment. And so that's establishing these dense 2D to 3D correspondences by predicting basically the normalized object coordinates of every particular object that's being detected in its canonical oriented space. And so that allows us to establish for every pixel in the image that's being detected as part of an object, where it should go in 3D space and in the canonical orientation. And so this gives us a bunch of constraints that we can use for an end-to-end per-cross optimization to solve for the object orientation here, as well as the object translation. And then we can also predict the scale of the object in order to get the full 9 degrees. So that we can also leverage these kinds of extra features based on these dense correspondences to inform the object retrieval. So that allows us to have geometrically informed features from the image in order to look up retrieval of CAD objects so that we can get this kind of full reconstruction of all of the objects in the scene here. And so this is what this looks like for a couple of example input images. We have the alignment of these particular objects that are not fully in the view. So there's a bit of occlusion here for this particular couch, I guess it is. And so we can end up with a more robust understanding of the object poses. And so also for this scene of a couple of chairs, and we get a more reliable estimate of the object poses in the scene. All right, so again, here we can see this bathroom scene, and we have a nice reconstruction of the object poses of all of the objects here. In fact, actually, the bathtub is a bathtub and not a sink, but that helps also with respect to the geometric estimates that are informing the retrieval here. So we can take a look at the CAD alignment accuracy. So this is basically a metric that if the object, it's focusing on the alignment. So if an object is within 20 degrees rotation, 20 centimeters translation, 20% of the scale of the ground truth, then it's considered to be a correct alignment. So this is what's being measured here on ScanNet images. And so if we introduce a per-crust optimization based on these dense predicted correspondences, we can already get an improved alignment accuracy here. But if we actually make this an end-to-end optimization, so now we can learn these correspondences such that they're most informative for this actually alignment task, as opposed to just correspondence prediction task that actually helps improve the performance here. And now we also introduce a weighting scheme in order to make it a more robust optimization. So correspondences have weights for which should be learned for those that are more reliable versus less reliable. And that allows for a bit of a performance improvement as well. And then finally, this includes all of the components together. So we can also take a look, that was an alignment accuracy metric only, and didn't consider actually any retrieval. So here we consider something to be accurate only if also the retrieved object is correct out of a limited database of potential objects here. And so here we can actually see an improvement when we do basically the alignment versus the alignment and retrieval jointly together in order to get a proper estimate of the object alignments in the scene. So something that's also kind of nice is that this method was trained entirely on ScanNet images and can still be applied to also other images. So here we have a couple of iPhone images, to be fair, of some sort of similar kind of scenes, but we are a little bit limited in the number of places we can access currently at the moment. So here you can see it does generalize decently well for some of these objects in the iPhone images that are captured here. So this allows us to leverage this nice strong priors from a fixed database of synthetic CAD models. Of course, there's a question here, this is going to depend kind of on the flexibility of the database to represent the objects that you intend to see. So can we relax some of these constraints potentially? And also what I think is particularly interesting. I mean, considering we are actually pulling objects from a database, there's more information than just the shape geometry. In fact, for like datasets like ShapeNet, we actually have their extension into things like PartNet that give us information about object parts, which I think is also a fundamental aspect to understand for reasoning about interactions and functions of objects. So I want to take a look at understanding object parts and scenes based on these synthetic priors that we now learn. So they have a strong basis in terms of synthetic object parts. We give them a little bit of flexibility such that they can actually fit more precisely to the scenes that are being observed. And so now we do actually have an RGB-D scan that's being reconstructed as an input here. And we want to be able to construct these part-based priors such that we can understand the decomposition of every object into its component parts, and also even for regions that are incomplete and not observed. So in the scene, you see there are some holes in the objects and potentially some stuff missing. So we want to be able to understand everything in terms of the object here. So this looks like this kind of problem setup where we have an input RGB scan, and that's been reconstructed. And so we want to be able to understand the decomposition of the object parts of all of the objects in the scene. And in fact, what I mentioned before, scenes are typically not constructed in a totally object-independent fashion. In fact, I would guess that all of the chairs in the scene are the same kind of chair. So we want to perform reasoning between all of the objects that we understand in order to get a more globally consistent representation of all of the objects here. So what we first do is to try to learn the priors here such that they're based on sort of nice, complete synthetic data, but flexible enough that we can now fit them to real data. And so what we have here is basically the part decompositions from synthetic PartNet data. And this is being trained in an autodecoder fashion to predict the individual part geometries. So this is basically predicting, for the location based on part latent code and the part type, what the SDF value is in terms of representing the geometry of the particular parts. So we also train one similarly structured for the global shapes, and that represents the shape geometry space, also trained in an autodecoder style so that we can learn to map latent codes to the full shape space here. And so now from an input scan and a set of detected objects, what we want to do is basically map these into their corresponding part and shape spaces. So each individual object here is being encoded in order to predict the object parts, basically the semantic structure of every single part type label that exists for that particular object. And we also estimate a part segmentation here. And then we can use that to project into the learned spaces that we've just learned with these autodecoders for parts and shapes, and immediately decode that in order to get the part representation. So that's basically a projection into the space here. But since we've learned a fairly nice manifold over the parts and spaces, we can actually go from these latent codes and perform a test time optimization to fit precisely to the observed geometry of what's being seen in the input scan. And so that means that we don't have to stick to things that are entirely sort of almost retrieved from the synthetic domain, but we can fit them to the real geometry. And that allows us to also perform joint reasoning across similar objects in the scene, which we assume are basically going to be related to each other. So in more detail, this looks like basically predicting the part structure for an object. So these are the semantic labels for all of the individual parts. And then from there, we basically learn an encoder that maps, predicts the projection into the learned part and shape latent spaces. And these can decode out directly based on the fixed decoders here. So these decoders are frozen and not learned at this point. And then we have a part segmentation that helps us inform the test time optimization. So here, and what we want to do is we want to be able to fit such that we have a global part shape consistency. So all the parts should still be globally consistent with a single shape. That's also why we're also predicting the shape in order to be able to still regularize this kind of optimization. And then we want to be able to do a sort of scene-aware optimization. In this case, what this means is basically looking for similar objects in the scene, so same class category and a similar estimated geometry, and they should actually agree with each other in terms of their part and shape decodings. And so this allows us to optimize across similar instances from the scene, because we have many of these chairs being observed from different views, so we see kind of different partial patterns across all of these shapes. And so that allows us to get this kind of complete part decomposition that represents the scene. So here you can see a sort of brief visualization of that optimization process at test time that fits to these particular scenes. And so it takes the initial predictions and refines them such that they fit to the geometry of the input scan, and that they fit together parts to shape and also across the shapes in the scene. And here you can see the interpolations of some of these objects in the part space, I think. Okay, maybe not. Sorry. Okay, sorry, the video doesn't want to play. Never mind. But you would be able to see the interpolation of some of the parts that they move smoothly. I guess you can see this a little bit in terms of the optimization, but we have a sort of intuitive morphing between different kind of object parts of different shapes. And here we have a quantitative evaluation in terms of these semantic part completion. So basically trying to predict the part decompositions, and also for missing regions that are unobserved in the original input scan because of just occlusions and partial views. And so this is in comparison to some state-of-the-art part segmentation approaches that have been typically presented in the shape domain. So for instance, like StructureNet. And this learned prior approach that allows for test time optimization, this allows us to get a more accurate representation of the objects. And we can also see a similar trend when we consider not necessarily the completion task, but just segmentation of the observed input geometry. So we constrain the evaluation to occur only on regions that have been actually observed in the input scan here. And here we also have an improved part segmentation performance on the ScanNet scenes. So you can see some examples in comparison to some of these other approaches that, for instance, StructureNet is predicting the part decompositions of the shapes as points. And we also have an instance segmentation approach, which is point group, but has been applied for part segmentation in this case, as well as another voxel-based approach to predict the object parts in a scene. And then you can also see that without the sort of scene-consistent optimization, you end up with some more inconsistencies between some objects that are similar versus the final optimization that allows for this reasoning across, multiple observations of similar kinds of objects. And you can also see this across the chairs. We have many different chairs that are observed in this particular scene, as well as several copies of the same kind of table And so that allows us to reason effectively about the different objects that we see here. And here you have just one more example of this scene where we have a sort of apartment kitchen scenario where we get a nice representation of the individual chairs and the table here, as well as some of the other objects in the scene. And so here you can see just again, that was supposed to be a video, but I'm guessing it's not playing either. Just a few more examples, basically, of understanding the individual objects and their part decompositions in the scene. So I think that's kind of nice, and we've now constructed this representation that allows for the flexibility of having some learned components that we can now fit to input observations, and that allows us also to construct this formulation where we can take into account the different kind of characteristics of individual scenes actually as scenes, so to start to consider similar kind of objects and how to reason about them, and in a slightly more holistic fashion than previously before. So I think that direction of moving towards a more holistic understanding of structures and objects, not necessarily just for similar looking kind of objects in a scene, is very interesting here. And we also have the opportunity to construct potentially a similar kind of approach in terms of understanding these kind of strong synthetic priors and fitting them to observations of what we've seen from the real world. And I think this also is a promising direction towards understanding sort of like this joint object recognition and tracking, actually. I actually did start my PhD originally in 3D reconstruction and tracking. I think this is a very nice kind of direction, of course, also very much related in terms of robotics applications, that we don't want to just do a bunch of post-processing on the scene. We want to be able to leverage this kind of inference in order to have feedback in the loop that can be responded to. And so understanding object poses, I think, has been shown by some works like SLIM++ to be an interesting potential anchor to do more robust tracking across different kind of challenging views. Also this, of course, semantic SLAM, to be able to understand all of the objects actually in a real-time scenario where we can actually react to what's being understood from the scene. And finally, a little bit in terms of understanding some dynamics and movement. I'm going to try this again, even though I know it's not going to work. I'm very sorry about that. No movement in my movement slide, but we can learn, start to learn similar kinds of learned priors to understand not just 3D object parts, but also deformable motion in objects, and to start to understand, because of course environments are not fully static. We need to be able to understand the movement and interactions within them. All right, so with that, I would like to conclude. Thanks for listening, and also, of course, thanks to my wonderful students here who have done most of all of that work that I've presented.
This is wonderful. Thank you so much, Angela. I think this was, first of all, a very big, broad picture of many very interesting topics, and wonderfully presented. I know it was a shame that many of the videos didn't play, but nonetheless. We welcome all of the members in the audience to type in their questions. They will be relayed to me and I can ask them live. Let me start with a question from Angela Scholing. In the work that you did from CAD to image alignment, when you said success, do you mean that success can be 20 degrees off? Was the metric designed to be that? And the accuracy rate is around 20%. Could you explain that more maybe this may not be sufficient for robotics is a concern that many people in robotics might have. A metric that people are okay in vision may or may not be sufficient yet for that problem to be considered solved for downstream tasks.
Yeah, no, that's a very good question. I mean, I think, of course, being able to show a sort of proof of concept that we can understand some of the object alignments is definitely far from, deploying it in a real robotic system further down the line. And I think there's still quite a lot that can be done from just, let's say, the pure vision perception. But to be fair, I think the single image scenario is more challenging than also what you would often see in the wild, which is a video stream, which would allow you to get a much more accurate location of the objects, whereas we have actually quite some sort of depth scale ambiguity of the objects that are being predicted. And that's not really being handled elegantly by an evaluation metric that just says, well, 20 degrees, 20 centimeters, and 20% of the scale. That's something that was designed following other approaches that did similar stuff in 3D, where perceptually the objects kind of look approximately in the right place based on this particular metric. And of course, there can be a lot more that can be done to improve this. And I think naturally there would be also this multi-view reasoning will allow us to get far more accurate poses. I mean, I think there's also something to be said about information that we don't fully leverage, which is, bringing that view of the 3D objects back to the images and comparing them to see how well they align will of course also potentially help to get an improved alignment there. But I think there's an interesting question that some of us who are in general trying to do 3D reconstruction are trying to handle is what is the right evaluation metric, and should it be geared a bit more towards perception, which is maybe what you want for things like content creation, or just in terms of hard accuracy, in which case objects might end up becoming a bit more blurry due to just the error and ambiguity that becomes averaged out in terms of predictions. So, but clearly also in that case, we would need a better uncertainty measure to handle this kind of scenario.
I think a follow-up question is from Florian Shkurti, and he asks, could you elaborate a bit more on the encoder-decoder for the object parts in the neural part primitives or NPP paper? Is there any supervision in the process? And a follow-up could be, how do we handle multiple hypotheses of what constitutes a part? So maybe you can go over this one by one or part by part.
All right. Yeah, so the part and shape encoding spaces that learn the latent part and shape spaces, these are basically MLP-based decoders. So very similar in the style of deep SDF. So basically a stack of linear layers and the coordinate-based representation that allows for fairly nice behavior in terms of interpolation through the latent space. The encoder that then projects from real scene data into that space is based on basically the 3D convolutions on the input SDF scene representation. And also leverages a graph neural network in order to predict the part graph structure. And in that case, I just mean the semantic labels of the individual part types. I think I've forgotten the second half of the question. Sorry.
No worries. I think the second half was what was the supervision, and then finally, if there are multiple hypotheses about what constitutes a part, how would you resolve that?
Yeah, so the supervision in terms of constructing the part and shape latent spaces, this is basically a self-reconstruction task on PartNet data. And then in terms of correlating with real world data, we have the annotations given by the scan-to-CAD work, which basically places ShapeNet objects into ScanNet scenes. And so that is in fact fully supervised there. Although it is a direction that we're looking into to relax that constraint and allow it to be somewhat self-supervised or weakly supervised, so that we don't have to rely on these fairly expensive annotations to map synthetic models into the real scene observations. In terms of multiple hypotheses, we don't handle them very elegantly. We just go forth and take one. I think in the RGB-D scan scenario, there's no ambiguity, but there's less ambiguity, especially when we consider the fact that also many times objects are repeated in the scene. And so maybe you don't see all of the parts from one observation. Often chair legs end up missing, but they'll appear in another observation of a different object, and that helps to reduce the ambiguity that we'll see in those kinds of problems. But of course, that's still very important. And I think for practical scenarios, you do actually want to be able to give an estimate of the uncertainty, of course, of the prediction, and also whether there are multiple hypotheses. And so I think there's a natural formulation there for classification type problems to just take the learned distribution out of the softmax. Probably something better can be done, but that can be done with the approach that we have already. And then estimating the geometric structure, the uncertainty there, that's, I think, an interesting question that we're also trying to figure out what is the most suitable kind of representation, because at some point a very low level kind of per location uncertainty value doesn't seem like, or it seems rather overly expressive, and we might want something that operates on a higher level basis than something like this. But yes, I think that's a very interesting question.
I think there are other questions as well. We are running out of time. What I'll do is I'll ask one more question from the audience. I also have one of mine, but I'll keep myself to the last. We have a question from Anas Mahmood, and they ask, what do you think are the main challenges of utilizing 3D shape priors for constructing 3D scenes from RGB in an outdoor setting?
In outdoors, I think there are some things that are very nice, and then of course some things that are more challenging with respect to indoors. I mean, I think, I might get the name wrong, the Virtual Kitty, I think, has CAD model annotations also for the cars. So that is also, I think, a very nice opportunity there, especially because, you know, the other thing is, outdoor observations, I think they usually come from cars. And so not only are they larger scale, so of course we have to consider how to extend representations that might not necessarily scale elegantly to that particular kind of scale. I think we can look to a lot of sort of graphics representations, hybrid representations for that. But one thing that is kind of interesting is that the cars will typically observe this always from the same kind of point of view. Basically, like, it will always be the left side of the street from the left-hand view and the right side of the street from the right-hand view, even though the sensor might spin on top of the car. So there are some kind of parts of the data that you'll never see, unlike indoor scenes where if you just take like a kind of arbitrary view of the camera across the scene, then you can be fairly certain that across, you know, a few hundred scenes, you will see all kinds of different views of objects. And I think that assumption doesn't necessarily hold in the outdoors. And so there might be some things in order to learn the full geometry of some outdoor objects that we need to learn more explicit knowledge of things like symmetry or stronger geometric priors for basically the other side of stuff that you almost never see.
I think we are towards the end of our thing. I have one last question, but I would like ask you a more open-ended question rather than a deeper technical question. In a lot of these problems where a lot of researchers, including Leo and Jitendra, have argued that we should really be seeing graphics as the inverse vision problem. And if you can solve that, a lot of the problems would become very interesting. In a lot of the current work in the last few years, we have seen that major progress in scene understanding can be made if we have good priors, maybe 3D models, maybe shape priors. Do you think that that is the right way to do this, that we should build bigger prior data sets so that we can do better retrieval? Or do you think we should work on scene understanding for objects where we are not basing our understanding on priors? Like, I don't have a 3D model of the scene. I'm actually building the 3D model of the chair in the scene and then aligning it.
It's a good question. I don't know if I have the right answer. I mean, I think there's a few components to that in terms of graphics and vision being inverse problems. Of course, this kind of makes sense. Although I think graphics has a slightly different, let's say, optimization than to be like the true inverse for vision, which is that it wants to be perceptually intuitive to people, and that doesn't necessarily always follow by like the input image scenario, which is truly photorealistic. And there's many things like people in general are very bad at understanding bad lighting or bad physics, where we can combine with things that are not truly realistic in a graphics kind of scenario. That's fine. And maybe that's okay also for a vision system, but maybe it's also not enough. I don't know. I do think simulation and this kind of stuff is actually kind of cool and allows for generating, you know, all kinds of different scenarios of data where in fact it's simply not practical to be able to collect and acquire that kind of data. And so in the end, that you probably need both, right? I think there are some areas where the current data is still kind of lacking with respect to just, you know, the progress and general quality that can be made, and doesn't mean that we should go around and collect all the things. I think there's definitely also some stuff that can be learned in, let's say, more self-supervised kind of ways. But we need that kickstart from a reliable annotated set of shapes, scenes, and so on in order to jumpstart the learning process so that it's in practice just more efficient to be able to learn this kind of stuff.
Oops. I think this is wonderful. Thank you very much for both the technical talk and insights. I think this would be a good time to stop. I'd like to thank you again on the behalf of all the audience members who are not visible to you, unfortunately. But this has been a wonderful interaction, and we would love to meet you one-on-ones. I think links have been shared with you. Otherwise, we'll follow up quickly through email. Thanks again, Angela. This is a wonderful line of work, and all of us are very excited to see what you do in the future years.
Thanks for having me.